Okay, so welcome everyone to this second webinar of this academic year, organized by the UK Quantum Fluids Network. My name is David Proman, and it's a pleasure to introduce today a talk given by Dr. Hiromitsu Takeuchi from Japan. So we continue these flow of talk webinars given by Japanese researcher, and thanks Hiro especially for accepting to give a seminar at this time of the day, which is quite late in Japan. So Hiro is a lecturer at the Osaka City University. Before being at Osaka, he went also to Hiroshima University, and then before that, Osaka City University again. His research topics are on quantum fluids and solids, topological defects, multi-component superfluids, and symmetry breaking aspect, and tachyon condensation. So a lot of theory on those topics, and today is going to give a webinar on based on some recent set of papers that he published, and the webinar is going to be on topological defects in easy axis nematic Bose-Einstein condensates. So please, Hiro, the stage is yours.
Thank you very much for your introduction, and thank you very much for giving me the opportunity to present my recent work in this nice community. So today, I'd like to talk about different kind of topological defect realized or predict in easy axis nematic Bose-Einstein condensates. And the contents of this talk is described in this paper. So if you are interested in this talk, please go to this paper. So, and okay, I'd like to start. And I'm sorry that to start by my private information. I'm looking for open postdoc for 3-year postdoc for my research fund in Japan. So research topic is dynamics of topological defect and spontaneous symmetry breaking, especially in multi-component superfluids. I welcome young researchers from different fields. For more details, please ask me my email, or I'm happy if you could circulate this information to any potential candidates that you may know. Okay. So first, I'd like to mention main message of this talk, the important result. We found some interesting vortex state in critical region of spin 1 Bose-Einstein condensation in the polar phase. And this figure show velocity field of the new vortex called quantum elliptic vortex. Vector field shows the superfluid velocity field of this around this vortex, and the background color show phase of order parameter of this system. As you know, as can you see that this vortex structure is quite different from conventional asymmetric quantized vortex written here. And when we see this vortex in 3 dimensions, for example, for conventional vortex, looks like vortex filament in 3 dimensions, while this quantum elliptic vortex looks like vortex band, like this. Okay, so this is outline of this talk. First, I'd like to talk research background by 5 pages, and second is on first main topic on quantum elliptic vortex. I'm sorry that I use video, which is used in the meeting of quantum fluid solid this year, but I think it's best way to save time. Okay, and the third one is second main topic on vortex phase diagram in the polar phase of spin 1 Bose-Einstein condensate. And at last, I'd like to make summary. And I would like to thank you, my collaborator, especially in we have a collaboration, experimental collaboration with Professor Sin's group in Seoul National University, and I also have theoretical collaboration with Taiwan group, Gary and Professor Go. Okay, let's turn to contents. So I'd like to mention my research background. I'm especially interested in study multi-component superfluid, especially superfluid 3 binary and spin-off Bose-Einstein condensates, because these systems provide a rich variety of physical phenomena, which are connected to different systems for condensed matter to high energy physics and cosmology because of the universal concept in the following, namely fluid dynamics, symmetry breaking, and quantum effect. And a harmony of these concepts enable us to access exotic and universal phenomena at the laboratory. Next, I'd like to introduce briefly the concept of spontaneous symmetry breaking. Here we describe a schematic of a typical phase transition of spontaneous symmetry breaking. First one is discrete symmetry breaking, sometimes called Z2 symmetry breaking. This symmetry breaking occurs, for example, in the ferromagnetic phase transition, described by real scalar field with double well potential like this. Here is x-axis shows the magnetization, and the y-axis shows the thermodynamic energy. The ground state, there's two ground states, namely minus m, minus negative magnetization and positive magnetization. And the energy is symmetric with respect to the change as of sign of magnetization, but ground state should have positive or negative magnetization, which mean the system broke, the symmetry, discrete symmetry broken spontaneously. And another example is symmetry breaking in superfluid or superconductor, which is described by so-called wine bottle potential or Mexican hat potential. The system has a symmetry with respect to rotation around the psi. Psi is a macroscopic wave function of order parameter of superfluid superconductor. The system has a symmetry with respect to the rotation around psi equals 0, but the ground set should have some finite phase with finite amplitude, which means ground set broken some sort of symmetry, rotational symmetry in the ground set. And according to this symmetry breaking, they happen, the topological defects can happen as a stable topological soliton. For example, here is a schematic of domain wall or kink. In the ground set, the order parameter should have real or negative or positive value. But between these two domain with positive and negative order parameter, the kink structure like this happen like this. This is simplest topological defect for these symmetry breaking. So another example is quantized vortex. Here is this arrow shows the direction of spatial gradient of phase, which represents superfluid velocity. And this line corresponding the phase singularity called vortex core. So around vortex core, we have a superfluid velocity around this. So this is stable topological request for the case of human symmetry breaking or rotational symmetry in the configuration space of macroscopic wave function. Okay, is in the this topological request can be nucleated via quenching transition, quenching phase transition. And such a mechanism is described so-called Kibble-Drake mechanism or Kibble mechanism. This mechanism originally proposed by Professor Kibble for describing defect formation in early universe, and later Professor Drake proposed analogy between cosmology and super system or other condensed matter system. And here I'd like to explain some typical scenario of this mechanism. Consider initially there's no symmetry, spontaneous symmetry breaking here. In disorder set in magnetic system. When we quench some parameter, for example, temperature, some dynamic potential become like this. Then when the symmetry breaking occur inhomogeneously in everywhere, order parameter grow independently like this. For example, when here we have a positive domain, but we have a minus domain here. Then we have a domain wall between these two domains with different sign in the magnetization. So a thick line shows domain wall like this. On the other hand, in the case of U1 symmetry breaking, we can describe this kind of picture. Here we can see the domain with different phases, and when the phase rotates pi around some point, we have a quantized vortex here. So this is a typical scenario of nucleation of topological defect in phase transition, spontaneous symmetry breaking phase transition. Okay. And very recently, experimental group in Seoul National University of the very interesting scenario of topological nucleation of topological defect in spin 1 BC. They consider some sort of quantum quench from antiferromagnetic phase to polar phase, and they observe this kind of characteristic picture. And according to this paper, they observe some complex complex topological defect called Vortex composite defect, described by this picture. Here we have a domain fold around this regime, which terminates at half quantized velocity, namely HQV here. And you can see this structure. You can see this structure in this picture, for example. Here, black regime shows the higher density of M equals 0 spin component in spinor BC, and here is domain wall, white line domain wall, terminated at half quantized vortex. Okay, and so this kind of structure has been also known in superfluid HEM3, and very recently, Helsinki group, experimental group in Aalto University observe similar structure. But today I'd like to focus on the phenomena in cold atoms. So, and we discuss analogy with this system in the paper. So, if you are interested in the relation between our system and HEM3, please go to my, please read my paper. But today I'd like to skip the relation in detail. So anyway, so I'd like to show next. I'd like to show the numerical simulation of this experiment to show what is mysterious in this system. So this is here. I'd like this picture shows the numerical simulation. Okay, initially we prepared the anti-ferromagnetic phase, namely A phase, where m equals 0 component is 0. So this state show A phase, and this is the density plot of m equals 0 component with some value of quadratic Zeeman shift. Okay, I'd like to play movie. Can you see the movie?
Yes, yes, we can.
Okay. I'd like to play again. I don't know how to. Yes. Okay. So this is a snapshot of the movie, and here is time evolution of m equals 0 component. Here is this is minus 1 component and plus 1 spin component. You can see that here is they appear domain wall like this. This is related to the Z symmetry breaking in the early stage of this dynamics. But you can see that core of inside or core of domain wall is occupied by plus minus 1 component here. And information of phase is also important. This is a phase of size m equals 0 component. Then you can see that phase jump by pi across domain wall like this. This structure is similar to dark soliton in scalar beach, which is known as unstable, dynamically unstable to decay quantized velocity. So we expect this structure should decay into quantized velocity, but as you can see that strange structure survive for long, as we observed in the picture in the experiment like this. So this is related to my motivation. So next, I'd like to show the fundamental property of this structure, namely quantum elliptic vortex. Okay. Next, I'd like to turn to the second part, first main part of this talk, quantum elliptic vortex. And to save time, I'd like to play a movie of a presentation at the QS meeting in this year. Okay, so I'd like to play. Just 12 minutes, I think.
Hello everyone. My name is Hiromitsu Takeuchi from Osaka City University. Today I'd like to talk about exotic vortex state in spinor Bose-Einstein condensates. This work has been already published in Physical Review letter here. First, I'd like to mention the main finding of this work. This figure shows the velocity field in the cross-section of a new vortex called quantum elliptic vortex. Vector field shows the velocity field around the vortex, and the background color shows the order, phase of the order parameter. You can see elliptic velocity field is quite different from conventional asymmetric quantum vortex. Okay, when we see this structure in 3 dimensions, conventional vortex looks like vortex filament, while quantum elliptic vortex looks like vortex band. Okay. This work is related to the recent observation of wall vortex composite defect in sodium spinor Bose-Einstein condensate by Sin's group in Seoul National University. This figure shows density distribution of m equals 0 component in the spinor BC for polar phase observed in this group. You can see that half quantized vortex here, which is terminated by a domain wall. This structure is quite different from half quantized vortex in antiferromagnetic phase, namely A phase. Here, white, this is a distribution of magnetization, and white and black spot show half quantized vortex, and this here is a pair of half quantized vortex. This picture clearly shows that half quantized vortex in P and F phase are completely different objects. And for simplicity, we call these vortices as a type 1 HQV and type 2 HQV, and today's target is type 2. Okay. To clarify the difference between type 1 and type 2, we show the vortex profile more clearly, in more detail. First, we discuss vortex structure in type 1. Let's see the vortex profile across this line for a single half quantized vortex, and the profile can be schematically written like this. Here, red and blue show the profile of m equal +1 and -1 component, and by removing vortex free component, we have a structure of conventional vortex in a scalar BC. Accordingly, we have circular velocity field around a single isolated vortex like this. On the other hand, the structure is quite different in type 2 HQV. This time we consider this cross section, and the profile in this cross section written by this schematically. And by removing vortex free component, we have a strange structure like this. And when we see this structure from top view, we have this structure. The important thing here is line singularity here, across which phase of the order parameter jump by pi. Okay. Therefore, velocity supercurrent can across this singular line. So the velocity field around type 2 HQV is quite non-trivial, and which is just structure related to quantum elliptic vortex. Okay. Here I'd like to explain formulation and parameter setting of this work. The vortex state is obtained by numerically minimizing Gross-Petersky energy functional written by this energy density. And we set a parameter as the actual situation of experiment by Seoul National University. And spin interaction energy is small positive. And the linear Zeeman term is 0, p equals 0. And the quadratic Zeeman term is positive, corresponding to p phase. And if the q is negative, the a phase is realized. The important thing is the ground state in the p phase written by this form, with just a complex scalar field, like a scalar conventional superfluid. Therefore, you may expect nothing interesting, non-trivial happen in polar phase, because the other parameter is complex scalar field in scalar BC, like a scalar BC. However, we found a very strange structure in vortex state. Such a vortex appear below some critical value for quadratic Zeeman term here. And above which we have a conventional vortex. You can see that for larger Q, we have a usual conventional, almost circular asymmetric vortex. However, when we decrease Q, the non-asymmetric structure is enhanced. And you can see that velocity field described by vector field form completely elliptic structure. Okay. And the important thing is type 2 HQB appear here at the edge of the elliptic structure. Okay. Another important thing is core of vortex in m equals 0 component is occupied by m equal plus minus 1 components, which have no velocity. Okay. To clarify the problem, we set two important questions. First one is what causes asymmetric breaking. Second question is what is physical mechanism to stabilize the elliptic structure. Answer to the first question is the spin interaction. The spin interaction imposes a restriction for winding number in the asymmetric state, described by this equation with cylindrical coordinate. And this restriction is described by the vortex winding rule, written by this equation. Okay. Let me see again profile in the cross section. You can see there is a vortex in m equals 0 component, while there is no vortex in plus minus 1 component. According to this situation, we can assume m equals 0 component has a vortex. The vortex must be non-asymmetric as long as both of m equal plus 1 and minus 1 component occupy the vortex core, corresponding to this inequality. Okay, and actually we observe spin density at the edge of the vortex core, corresponding to the vortex winding rule caused by spin interaction. Okay. Let's turn to the second question. To understand the facts of this phenomenon, we introduce phenomenological model extended from potential flow theory hydrodynamically. In the Joukowski mapping in the potential flow theory, circular configuration is mapped into elliptic configuration. Accordingly, circular conventional quantum vortex is mapped into elliptic vortex like this. And the energy of elliptic vortex can be computed by these two terms. First term comes from elliptic velocity field called hydrodynamic potential, which causes expansion effect along a long axis. And the second term comes from the tension of the soliton, which occupies long axis. And this soliton called F-core soliton, described in this paper. Therefore, the answer to the second question is balance between the soliton tension and the hydrodynamic potential. Okay. Finally, I would like to show critical behavior of quantum elliptic vortex. This plot shows the length q dependence of the length of long axis of elliptic vortex. And red circular mark shows numerical data, and black solid curve shows theoretical plot. You can see that length of the long axis diverges as like this for small q. This scaling behavior is supported by soliton tension with elastic correction term written by red term. Next, we show local ordered state in the vortex core. This plot shows the density of m plus minus 1 component and spin density and spin interaction in the core. And anyways, the important thing is continuous phase transition from conventional vortex to elliptic vortex is described almost perfectly by a simple Ginzburg-Landau model, characterized by the density, total density in the at the vortex axis, written by this form. So, and this phenomena can be understood as a local phase transition to the AF phase. Please come to my poster on Wednesday for more detail. Okay, let me summarize. Type 2 HQV are stabilized as a quantum elliptic vortex in the polar phase. The spin interaction causes spontaneous breaking of asymmetry of a singly quantized vortex in the polar phase with small quadratic Zeeman energy. An elliptic vortex is stabilized by the balance between spin interaction and soliton tension and hydrodynamic potential. Lastly,
okay, this is the end of the first main topic. Here I'd like to hear a question if you have. If no, I'd like to continue. Okay.
Yeah, Hiro, we can maybe take all the questions at the end at this point.
Okay. Okay. Okay, I'd like to turn to next. In this topic, I'd like to maybe phase diagram of Bose in the polar phase of spin 1 BC. And we also show the phase diagram soliton related to the recent observation in Heidelberg University. Okay. So main finding of this work is phase diagram Bose in the P phase, polar phase of spin 1 BC. This is phase diagram of spin 1 BC with 0 linear Zeeman term corresponding to the experiment in Seoul National University. And here is x-axis shows a quadratic Zeeman shift, and the y-axis corresponds to the spin interaction energy. And we found this vortex phase diagram here is so here is p phase. I'm sorry. So this is our target, p phase. Okay, and this is the phase diagram of Bose. And we have found 3 characteristic vortex core structure in this phase, in the p phase. First one is antiferromagnetic core with non-asymmetric structure. And the second one is ferromagnetic core, namely FC vortex, schematically written by this one. And this is just a conventional vortex. You can see in scalar BC or superfluid M4. The core is occupied by just normal state. But other 2 vortex, we have different order set. For example, as I show you that here is a different ground state depending on the parameter. And in this vortex, we have different ground state in the core of Bose like this. Okay. So here I'd like to explain the background of this system. What is novel in this system? The ground state in the p phase written by this form, which means order parameter is complex. Order parameter in the ground state is complex scalar field, like conventional superfluid, such as superfluid Helm 4, scalar BC, S-wave superfluid, or superconductor. So we may expect nothing interesting happen in this system because we know the topological defect in scalar conventional superfluid. However, answer is no. In the p phase, there appear various type of Bose and soliton, as we discuss, for example, quantum elliptic vortex. And today I'd like to mainly talk about Bose, this paper. And we mentioned briefly a study about soliton here. Okay, this so this phase diagram represents a phase diagram of core structure of singly quantized vortex. In the previous work, we focused on the parameter regime of sodium condensate described by this blue dot line, and quantum elliptic vortex appear in this regime. And but we by extending order parameter regime in the fourth regime of polar phase, we found this kind of phase diagram. Here, red broken line shows a second order phase transition, and this line corresponds to the first order phase transition. And this is different phase in the ground state, BA phase. So this is a phase diagram. And in this work, we investigate the impact of quadratic Zeeman sect and spin interaction on the singly quantized vortex in a systematic manner. Okay, next, I'd like to show the typical structure of AF core vortex and F core vortex, which was obtained numerically. Before explain this structure, we would like to introduce Cartesian representation written by this form. Here, order parameter in this representation is originally, I think, introduced by this paper, and they consider analogy between spinor BC and superfluid Helm 3. So I think researcher from superfluid community of superfluidism 3 know D vector in superfluidism 3. And this D vector is analog of D vector in superfluidism 3. And in the case of zero magnetization, zero spin density, order parameter can be represented by this form. Here, D vector is a real scalar, a real unit vector, and N is the density of the condensate, total density of the condensate, and theta is the phase. And the polar phase, P phase, corresponds to this state, namely easy axis nematic, because we use term of nematic because this D vector can mimic the property of nematic order in nematic liquid crystal. For example, if we turn sign of the D direction, turn the direction of D into the opposite direction, and simultaneously we change phase by pi, order parameter remain the same value, which means direction of D and the opposite direction can be identical when we consider phase rotation by pi. This means this vector can mimic order of nematic liquid crystal. And in the polar phase correspond to the easy axis nematic order. On the other hand, AF phase, anti-ferromagnetic phase correspond to the easy plane nematic order, like this. Okay, and this is a numerical result of cross section of elliptic AF core vortex, namely AF core vortex. This shows this velocity vector field shows a texture of D vector, and the color of vector shows the color of phase of this value. You can see that in the bulk, D vector is along Z axis, correspond to the P phase. And a question? No. Okay, sorry. D vector correspond to the P phase. While in the core of vortex, we have F phase, which means vector lie in the XY plane. And you can see that vector turn here to the opposite direction. Simultaneously, phase jump by pi, which means here nematic order parameter change continuously here, no singularity here. Okay, which make possible to realize half quantum vortex here and here. And we have a spin density according to related to the vortex winding, breaking vortex winding rule. Okay, and this structure we explained this structure in the last topic, but I'd like to focus on this structure next. And this is a typical structure of asymmetric F-core vortex. This vector field corresponds to the D texture, and this is a texture of spin density. In the bulk, we realize polar phase, but in the core, we have magnetization, which broke nematic spin order. This order parameter is ill-defined in the core. And we have characteristic spin texture like Marmin-Hall texture known in the superfluidism 3. But spin density disappear in the bulk. So it means this Marmin-Hall texture is localized in the vortex core. Similar structure has also been observed numerically in this paper in the Topological system, but they did not consider the influence of quadratic Zeeman shift systematically. But if you are interested, please read this paper. So next, I'd like to show the phase diagram soliton in the polar phase. So here, this is the phase diagram, and this here is the polar phase. And we also observe different ground sets appear in the core of soliton. This is a typical structure of soliton obtained in the polar phase. This is a conventional dark soliton. Here, blue dot line shows the profile of psi m equals 0 component, and red and broken green line show +1 and -1 component illustrated here. So this is a conventional dark soliton. We call normal core soliton. We call this structure as a normal core soliton because normal state realized in the core. On the other hand, in this case, we have AF core structure with non-zero +1 and -1 component. But this state has no spin density. On the other hand, for the BA core soliton, we have spin density in the XY direction. And for F core soliton, we have spin density in Z direction. I'm sorry, this is the profile of total density and spin density. Here we showed spin density as a F. So Fz is density in the Z direction, and F perpendicular corresponds to the spin density in the XY direction. Okay, and we have obtained this kind of structure. And very interestingly, some of them have been observed experimentally at Heidelberg University. I cannot explain detail here, but I would like to explain detail of this picture observed in the experiment, detected in the experiment. Here, this picture shows a collision of two soliton with zero magnetization. And here is y-axis shows the time, and this is x-axis shows the position. So when two soliton collide, they observe magnetization in two soliton, plus magnetization and minus magnetization in the longitudinal direction. And this soliton with magnetization correspond to the F core soliton, I think. So I mean this prediction. So this structure has been also observed, this soliton. But I'm not sure whether the initial soliton is AF core soliton or BA core soliton, because they did not observe the spin magnetization in XY direction. So I'm not sure, but this clearly shows that F core soliton appear actually in the experiment of gold atom. Okay, let me summarize. So we discussed wall vortex composite defect are realized in sodium condensate in Seoul National University, and type 2 half quantized vortices are stabilized as a quantum elliptic vortex in the p phase of spin 1 Bose-Einstein condensates. And we repeat phase diagram Borsci and soliton in the polar phase, theoretically and numerically. So that's all. Thank you for your attention.
Thank you, Hiro. Thank you very much for your interesting talk. And I can definitely tell you that this is the first time that we have a video inside a video. Let's say a speaker in a video inside a webinar, definitely. So, so thank you also for doing that. Are there any questions for Hiro? Please just feel free to unmute yourself or type in the question, type the question in the chat, and I will read it. Well, maybe I can start to ask a question. So I'm curious to know what could be the dynamic of these type 2 HQV wall vortex that you described. So and I'm curious in the experiment that you're showing in the summary slide. Did they observe did that vortex wall move and rotate in the cloud, or does it stay still?
Yeah, it's difficult to observe detailed dynamics, but according to the numerical simulation and many snapshots of experiment, we observe two type of states. I mean, as you know, so domain wall terminates at a half quantum vortex, but there's a two possibility of half quantum vortex, namely plus sign or minus sign. And if we have a composite defect with two positive half quantum vortex, which can rotate or can be stationary. However, for the case of composite defect with two opposite sign of half quantum vortex, which propagate like a vortex pair of with opposite sign, right?
Like a dipole.
That is observed in experiment and numerical simulation. Yeah.
Thank you. I think we have a question by Magnus.
Yes, I think maybe you partially answered it already now, but just to check that I understand, your quantum elliptic vortex, can you not understand that essentially as what David said, as a dipole of half quantum vortices?
You mean what is different between dipole? Sorry, say again,
the elliptic vortex. Is that not, can you not understand that as a pair of half quantum vortices with opposite circulation?
So that's, yeah, that's important.
Sorry, with the same circulation, yeah.
Yeah, that's the important point, because as I explained, not here, this next part. Yes. Okay. So as I explained this slide, the velocity fields between type 1 and type 2 is quite different. And most familiar HQB is this type, I think. For example, I think this is a famous picture, famous experiment to observe half quantum vortex, and this vortex corresponds to type 1 half quantum vortex. However, this vortex corresponds to type 2 half quantum vortex. And as I explained, so this kind of structure make superlative velocity fields different, quite different from this case. So I mean, it's not correct to understand elliptic structure as dipole of half quantum vortex. This is my opinion. Okay.
Okay, thanks. Can I just follow up on that a little and ask you, with this picture that we're seeing now, if you look at your type 2 HQV, what is, so when you showed the elliptic vortex, you also showed that you have a magnetization at the foci of the ellipse. And these are oppositely pointing, one in the plus y direction, one in the minus y direction.
Yes.
So what if you do a basis transformation of your spinor basis so that you, instead of quantizing along the z-axis, you quantize along the y-axis? Then what do the density profiles look at in the 3 spinor components that you now have?
So you asking about this structure, right? This structure.
Yes, exactly. Yes.
So you mean we can rotate quantization axis in the space, but in this system we have a quadratic Zeeman shift. So such rotation costs energy. So this is only the stable. I mean you mean rotation in XY plane? Or
yeah, I just mean rewriting. You can write your spinor components corresponding to quantization along any axis you want, regardless of which way the magnetic field points.
Yeah, so rotation in the XY plane is okay, because which is not related to the quadratic Zeeman shift, but rotation in the YZ plane or XZ plane cost energy, so it's forbidden energetically.
If you wrote it, yes. Okay. Sorry, I'm not going to take up all of the time here, but we can discuss it later, maybe in some way.
Sorry.
Well, I think I understand your point anyway. Thank you.
Thank you, Magnus. Any other question for Hiro? Well, I also have another question, if I can. So everything that you've shown us is essentially in 2 dimension, if I got it right. So what is going to happen if you're in 3 dimension? I mean, I'm just referring to the sketch that you had in your first opening slide. So yeah, exactly that. Yeah. So have you got any idea already?
So this is a 3-dimensional simulation of stationary state in a trapping system. So this shows this kind of 3-dimensional structure is stable. And if we excite this state, we can expect this kind of perturbation, like wrapping band. So such as this kind of structure can change qualitatively the dynamical behavior of a vortex. But I'm not sure exactly, but some sort of such kind of effect has been discussed in the literature of superfluid 3. Because behavior of this vortex can be similar to the behavior of double core vortex in the superfluid 3. But so far, they discuss such a vortex as a dipole of half quantized vortex. But such a behavior is different from vortex one, because velocity field should around this band structure. So I'm not sure what is difference between dynamics of double core vortex on the vortex band. It should be interesting to study more about the dynamics of in 3 dimensions. Thank you. Thank you for your question.
Thank you, Hiro. I think we have Samuli with a question.
Yes, thanks. So it's maybe not a proper question, but But just a comment on the helium-3 stuff. So I think there are recent experiments published by the Helsinki group also on these, they call them kibble walls or something like that. So basically there is in 3 dimensions. So basically there are 2 rods and then this kind of planar structure between them in 3 dimensions. I'm not sure whether this is exactly what you meant, but just thought it might be worth mentioning. So this is in the aerogel experiments in the polar phase.
Yeah. So thank you. Yeah, I know a lot of interesting contribution from Old University. Yeah, thank you.
Yeah, thanks.
Are there any other questions for Hiro? Okay, so if not, it's maybe a good time to wrap up because it's getting really late in Japan. Thank you, Hiro, once again to talk about your recent set of works on this topic. And I should also say that the next webinar is going to be probably on the 23rd of November, but we're still waiting for the speaker to confirm about that. So more information will come soon. And then it's likely that we're going to have the other 2 webinars later in December the 7th and the 14th of December. But more information will also come on the UK Quantum Fluids Network webinar webpage. So thank you for attending this webinar. Thank you, Hiro, for presenting your work, and see you probably in 2 weeks.